Hello everyone, Jeb from Jeb's Project. Let's see what we have on the bench today. On the bench today we have an MFJ 260 300 watt dummy load. It's supposed to be able to take 300 watts for 30 seconds and 100 watts at about a minute and a half, and then only about 25 watts constant for over 6 minutes. Well, the dummy load has worked good for quite a while, but I need something that'll do. This is supposed to go up to 650 megahertz, but it doesn't. It really doesn't. Hook it up to the dummy load. Let's turn it on. Alright, we'll bring her down into the nano VNA here. Let's see if we can. Okay, right now that's 1 to 30 megahertz, which is good. 1 to 30. We've got an insertion loss of about minus 40 dB. Okay, that's not bad. That's pretty good for the dummy load. But let's start going up in frequency. Stimulus, stop frequency. Let's go to 60 megahertz. That's for 6 meter. Okay, we've got an SWR. Let's see, and it's 60 meter, 1.073. Well, for 6 meter, that's not bad. That's at 60 megahertz, but we're at minus 29 for the insertion. Say, let's go up to 200 megahertz. Whoop. Yeah, she took off pretty bad. It's over a 2 on the SWR and minus 9 on the insertion, which isn't good. That's way too high. So this is only good for 1 through 60, or 160 through 6. It worked just fine. It's decent, but when you want to get up into 2 meter and 440, that's not very good. It just will not work well. So we're going to take and see if we can't build something better. Alright, to start off with, there's plenty of YouTube videos out there on 250 watt dummy load, but a lot of them don't show using the nano VNA and the spectrum analyzer of the characteristics of it. Some of them are using wire to feed the resistor. Some use direct connection, the SO239 or the end connector, directly to the resistor in order to get to higher frequencies. But that's I want to be able to make it a dummy load with a 40 dB tap off of it. So that's what we got this little box for. We'll mount this right to the top of the heatsink. First, let's take a look at the heatsink. This is a pretty good size, a pretty good massive heatsink. These came out of I believe, some sort of amplifier. Got them from a friend. I've gotten a hold of 2 of them. They're about 3 feet long. I cut one off here. And there's another set that I got that's got more pins. But this one here is quite sufficient for a 250 watt dummy load. This should be more than sufficient. And then we'll mount this aluminum box on the top, put a BNC connector on this end and an SO239 over here. But what we're going to use is a bulkhead, SO239 bulkhead. I should use an N, but this being low power, a 250 watts constant. This should be okay with the BL259. It'll give me a little trouble on the high end, but it's got the cable, RG 316 cable, which is good for UHF and VHF. So we're going to use this to get to the resistor. We'll mount the resistor off the cable here down, and once it's mounted in the box down here someplace, we'll put this in and bring the cable directly to it, so that we keep our distance short, as close as we can, without limiting us to where we can mount it in the box. And with the cable, it gives us more options. And then of course the BNC over in this side to connect the three 820 ohm resistors from the center feed here to here. So that, and then of course the 100 ohm to ground. That should give us our 40 dB attenuation. I don't have the resistors yet, but I figure somewhere around in there for the resistor with the connector here, with the bulkhead here. That'll give us our connections on both ends. When we're done, I'll take the whole unit, I'll put the nano VNA on it, see what our SWR and our insertion loss is on it. That's if I've got that correct. We should be pretty good. I've already tested. Now we got our box mounted. We only put 2 screws in because we really don't need any more than 2 screws. All we're using this for is to get it mounted down to the heat sink, so that it'll make contact and dissipate the heat. So I know it should probably use 4, but 2 is more than sufficient with some heat sink grease underneath of it. And it's pretty much mounted center of the heat sink and centered this way. Even though our resistor is going to be off center just a little bit, it should still be okay. The resistor will be right over top, if everything goes right, one of the pins. So, well, we'll get to drilling and mounting the bulkhead. Now, one thing we do have to do is our 2 holes are drilled. They've got burrs on them, so we'll need to clean them up a little bit. We'll countersink them just a tad, just so that we don't have any burrs sticking up. There, and that'll allow the box to sit flatter. Okay, now that I got my holes drilled, this is for my SO239, this is for my BNC, and then my 2 mount screws. Basically, up for center and pre-drilled, and then used a step bit right here to take and drill my hole larger. Same here. Okay, we'll get her mounted and start putting stuff in. We'll take some heat sink grease here, some thermal compound, and put underneath that and mount the box down. Okay, I'll take a little bit of thermal grease here, cover the bottom of the box with it, so that we got a nice thin layer on it. Don't need to go overly hog wild on it. You're just trying to fill in the little voids. So we just put it on there at a nice, smooth, even layer. It's going to take quite a bit. So we'll open up the container again, grab some more. We'll put it on there and start spreading it out. Try to cover the whole bottom. That way you can use this as somewhat of a heat spreader as well, even though aluminum's not overly good for heat spreader, but we'll use this aluminum box as a heat spreader as well. So there we go. Now we got a halfway decent amount on it. If you notice, it's not gobbed on there, but it's a nice even layer. That way it'll fill in any of the voids between the box and the heatsink. So let me get the lid back on this messy stuff so that it's not getting all over the place. Let me get a rag, wipe my spatula off. There we go. This stuff is messy. Just got it all over my hand already. Okay, we'll flip her over and set her down. And I'll put the screws in it. Oh, almost knocked my coffee off. Okay, we'll get this one put in. We'll get her tightened down. Snug her down as tight as you can without snapping the bolts. There we go. Gets us a nice, you see right in here where it's starting to squeeze out a little bit. She's starting to squeeze out all the way around. That's good. That means we got the whole bottom covered. Alright, I'll be back when I get the bulkheads in. Okay, well now I got our SO239 installed. With the, we used a through hole. We didn't use a bolted style because I wanted this coax. So we take this, bring it down to the resistor, ground it at the resistor, and center to the course to the pin. Try to keep as much stress off that tab as possible. My 40 dB resistors from here to the tab. Hoping I've got enough room. I don't have the resistors here yet. I do have some. I could probably estimate the distance. I don't have the correct values, that they're on their way. But we should be ready to start mounting the resistor now, the 250 watt resistor. This is the only disadvantage that I can see so far to this is it's using a 50 ohm 250 watt resistor, where the MFJ has a tube resistor, and they can usually dissipate heat quicker and usually take a little more power. But this 250 should be fine once it's mounted down here and the resistors here. Once it's mounted to the heatsink, it should be good. We'll find out. We'll be doing some temperature testing too. See how long it goes before we hit 100 degrees Celsius. Because according to the data sheet, the max temperature before it gets drop off is 100 degrees Celsius. So that's about 212 degrees Fahrenheit. So hopefully this heatsink will keep the temperature down. We'll be doing some testing right on top of the resistor so that we know what the temperature is at the resistor itself. Okay, be back when I'm ready to mount the resistor. Okay, now that we've determined that we need about that much room for our resistors for our attenuator, got the resistor mounted. I don't have any heat sink grease on it yet, any thermal grease on it yet. I haven't gotten that far with it, I just got it mounted. And then we got to take and cut the coax right about here and strip it back a bit, fold it over, solder it to a tab right there so that it comes across and solders the ground's right there and the tip touches right there. That'll keep the distance as short as possible outside the coax. Alright, let me clip it here. I'll cut it off, and let me go ahead and do that right now. Okay, we need it right about there. Okay. There we go. Now I'll have to take the bulkhead out, strip the casing back to about here, fold the braid over and solder it, and then open the tip up just a little bit for there. Alright, let me get it stripped back and then I'll bring it back in when I'm ready to solder it. Okay, well, what I've done here is I stripped it back a little bit, took in, let's see if we can get a little better. Yep, and took a loop, undid it, or spread it out, and soldered the shield right straight to the loop, and opened up the tips, and only this much of the wire is sticking out of the coax, so that keeps our distance nice and short. So let's see if it fits alright. Get it put back in here. And now let's get some thermal compound under it. Let's take it loose here. 2 screws out. Let's dig out our thermal compound. And find what I did with my spatula. Oops. Not sure what I did with it. Okay, I'll take a little on my finger. Throw some on there. Put her down in there and we'll get her bolted down. Take a rag clean off my hands. Get this closed back up so it's not all over the place. Let's get her bolted down. Next thing is to get this loop. Tighten that down as far as I can. There. Now the next thing is get this down to the tab. Okay. Seems to be good and tight. Let's fasten our connector back on. We don't need the lock washer. We've got the star in there. Come on, get a hook back on there. Okay. Bolt it back down. Okay, there's that. Now let's solder the tab to the coax. Well, we should be at the point that we can test it at least. Let me get some of this stuff out of the way, get the Nano VNA hooked up. Okay, this is the sweep for the MFJ 260 300 watt dummy load. Down here on 1 megahertz we're at 1.09 at minus 46.9 dB return loss. 2 is set at 240 or at 145. That's a 2 meter. It's 1.45 SWR at minus 14. We can't even get it down below the minus 20. The 70 centimeter band at 435 is a 12.9 SWR with a return loss of 1.34. Well, that is terrible. They claim it's supposed to go to 650 megahertz. It doesn't. Okay, now let's compare that to the DIY dummy load. Let's hit the set reference. Let me switch over to the DIY. Okay, connected to that and sweep. Okay, as you can see here in red is the MFJ. Here's the DIY. Now that's without any inductors or anything, we're just plain connected. At 1 megahertz we're at 1.004. At 145 we're at 1.05, and at 70 centimeters 435 we're at 1.46. So we're a whole lot better than the MFJ when it comes to the return loss and SWR. The return loss though on 70 centimeter is only 14.5. I'd like to have that below 20. Okay, now we'll put the resistor in, the resistor pack. First we've got to figure out how long we need it. So, yeah, by the looks of it, just nip it off right there at the end. Slide that in there, right in the end of the, bring it out, rest the resistor, whoop, if we can rest the resistor there. So we'll have to, I know they aren't the 820 ohm, but I don't have any at the moment till I get some. When I go to build the 500 watt unit, I'll have the 820 ohm. Should wind up with just a little bit more than 40 dB. We'll find out for sure, because we'll be testing that here shortly. Okay, now that we got it soldered there, soldered on the end of the BNC. There. Now we'll take our 50 ohm, which I've got two 100s to make our, it's supposed to be 52 ohm or 51 ohm, somewhere in there, and we'll clip that off. plug that right onto the ground tab. There, I'll give us our 50 ohm to ground. And we have our little capacitor there, or our metal tab down the side of the resistor here, so it can be adjusted for capacitance, which is supposed to help on the upper end. Alright, let me get the spectrum analyzer set up, and let's take some readings. See if we're 40 dB down. We should be probably, I think, I'm going to take a guess at 42, 43 dB. Well, let's take a look. Okay, let's start with frequency. Let's do our span. We want to start frequency at 1 megahertz. We want a stop frequency of 500 megahertz. Okay, there's our start and stop. Now we need to turn on our tracking generator and take and connect our two cables. One coming off the tracking generator output and the other for the spectrum analyzer input. Okay, now that we got the two cables connected, let's normalize. Oh, gotta turn it on. Yeah. Okay. Then we'll normalize. Okay, now that we have it normalized, we'll disconnect the two here, or disconnect the barrel. I know this is going to insert some loss, but not a lot. We'll hook this up to the input, and we'll hook this end up to our attenuation. Okay, according to that, we're at 40 dB. 40 dB attenuator. Okay, here's 40 dB right here. And we're right at the 40 dB mark. Okay, now let's take a look at the MFJ. We'll just unhook this here. Unplug this end. It seems to be pretty flat across there, which is nice. Oof. Dang this. Okay. Now we'll take the MFJ up there, and I have this one here, and we're right at 40 dB. Okay, let's start out and get our base temperature here. It says 28.4 degrees Celsius. Let's switch over to Fahrenheit. And we're at 82.5. Now that seems to be a bit high. 81.6. Okay, that's our start temperature. 81.6 degrees. We've got the radio sets for 50 watts going into the dummy load, and we have 50 watts. The resistor's starting to heat up. We'll give it a minute. We need to make sure we stay under 212 degrees Fahrenheit, which is supposedly 50 degrees Celsius. 81.6. And we'll have something right there. There, 99 degrees. 94. 96. 107. Okay. 108. 109. $111. $112. She seems to be staying right around 112 degrees. And it's been a minute. 113 degrees. So she's staying right around 115. So she's staying right around, that's at 50 watts. And that's over a minute and a half. The MFJ is only supposed to handle 25 watts at a minute and a half. The heat sink is still cool. Let's take a look at the resistor now that the power's off. 88. 87. So it didn't take long at all for that to cool down. That's really cool. Alright. So 50 watts, it'll handle that without any problem. Let's take it up to 100 watts. And we'll give that a test. Okay. We're at 87 degrees. Okay, there's 100 watts at it. We're up to 125 degrees already. $129, $130, $133, $142, 43, 44, 45, 'kay, that's over a minute, and it's at 148 degrees. I'd say that's well below the 212. And she's already cooled off to the point that she's touchable. That heat sink's doing a real nice job. Doing a real nice job. Okay, well, I would say comparably, that's a whole lot less money for a whole lot more dummy load. That's really nice. I'm going to build a 500 watter. This 250 watt will do more, or be more than sufficient what I need. Covers the bands I need. It's got the attenuator I need now, and it's all in a nice little, neat little package. Not much bigger than the MFJ. So I've already got somebody that wants me to build them one, and well, I've got the heat sink for it, but and I've got the resistor for it, and I've got the connectors and the resistors. So having all the pieces and parts, I probably will build them one, but I want a 500 watt, because that'll do more than a kilowatt. PEP. This one here, supposed to, according to the data sheet, about 10 times the resistor value at 250 watts, but PEP is about 10 times more, so that's 2500. I don't think I'd ever try to hit that with 2500 watts, even PEP. The most I plan on hitting that with is about a kilowatt, probably. So, alright, there we go. The MFJ didn't stand a chance. Alright, you all have a good one. Please like and subscribe, and catch you in the next one.